Hello everyone, and thank you for joining us for today's Surface Measurement Systems online workshop. Today we'll be exploring the topic using advanced sorption methods for characterizing porous materials. And we're very thankful today to have as an official partner and collaborative host with this workshop is the University of Manchester, who will be hearing from Dr. Xiaolei Fan later on in today's session. So a big thank you to Dr. Xiaolei and the University of Manchester for helping us arrange this workshop and the content therein. Before we proceed to our first session, I'd just like to remind our audience that we will have 3 live Q&A sessions throughout today's workshop, and there are 2 ways you can take part in these. You can submit your questions in writing using the questions tab in the webinar control panel, or if you would prefer to raise your hand and ask the question over your microphone, please raise your hand when prompted to in the Q&A session, and I'll let you know when you can unmute your microphone. So effectively, raise your hand and I will unmute you, let you know when you can talk, and you can ask your question directly to the speaker. So once again, you can submit your questions in writing in the questions tab, or you can raise your hand when it comes to the live Q&A session and I will unmute your microphone. So moving to our first session for today, and our first speaker, we're very lucky to have with us Dr. Vladimir Martis from Surface Measurement Systems. Dr. Martis is the DBS Product Manager for Porous Materials and Vacuum Product Specialist at Surface Measurement Systems, and he received his Master's degree in Materials Engineering from Trenčín University of Alexander Dubček in Slovakia in 2004. He received his Engineering Doctorate degree in Molecular Modelling and Materials Simulation from the Chemistry Department at the University of College London in 2012, with the thesis title Synchrotron Radiation Studies of Multi-Component Metal Oxides. Since joining SMS, Vlad has continued to work on the development of advanced in situ experimental surface science technologies using molecules as probes instead of X-rays for studying catalysts, zeolites, MOFs, polymers, freeze and spray dried materials, composites and glasses under relevant industrial conditions. Vladimir has authored several papers in peer-reviewed journals and presented at several international conferences over the years. So he's very much a leading expert on this area, and we're very lucky to have him with us today to share on this topic. So without further ado, I will now hand over to Vladimir.
So thank you very much for the introduction. And so today I'm going to talk about the characterization of porous materials. Okay, so first let me just give a short introduction about the absorption processes. So I just want to set a little background. So you might be so absorption is quite widely used process in industry, and there is several applications for using the adsorbents in industry. So for instance, the adsorbents are used for dehydration and purification of gases by adsorbents. So for this kind of application, we use carbon molecular sieves, zeolites or silica gel. So what you see here, I got a picture of the moisture trap. You probably find this moisture trap in your gas lines in the lab. So if you look next to a TGA, GC or TGA, so typically this instruments require dry gas. So you might find the moisture trap like this filled in with zeolites. And what you can see, some of the beads have different color. So this bead basically will tell you when the material is saturated with water, so it needs to be replaced, or basically water needs to be removed by heating up to elevated temperature. The other example is silica gel. Silica gel you can find in many day-to-day things. So for instance, light gauge electronics. Basically, the role of the silica gel sachet is to keep the materials or electronics dry. The other important application, which came up recently, is direct air capture. So basically, we try to remove the CO2 directly from the air. And we had a picture of this fan. So this is the process developed by one of the company in Switzerland when you use these fans. So air gets sucked in, and you have a solid adsorbent, and the CO2 is trapped in, then heated up to a certain temperature and released. So how this adsorption process actually works? So in this case, so we use in all these cases like 6-inch gel and that's zeolites when they use for dehydration or purification. So it's based on the pro molecules like water. So basically, we can use the water. And so what's happening when the adsorption process takes place? So you have the vapor molecules interacting with the solid adsorbents. But there are 2 processes can happen. One molecule can get weakly bonded to the surface, so get absorbed. So we usually talk about the van der Waals forces, or they can penetrate into the bark, and then we talk about absorption. This is typically for polymers. And then the rest of the molecule coming out. So this is typical absorption cycle, which takes place during adsorption experiment. And during the desorptions, when you reduce the concentration, what's happening, the molecules which are actually weakly bound, they can be dissolved in the process. So we have so what we really want to know in terms of these materials, we want to understand the absorption properties of this material. So we want to know how fast these materials are absorbing the water or gases, and how quickly we can release these molecules. And in terms, when you're talking about the absorption isotopes, there are two major techniques. So one is volumetric absorption apparatus, the other one is gravimetric absorption apparatus. And the difference between these volumetric apparatus is basically static method. So it's used typically nitrogen is used as a probe molecule, and you obtain data like surface area and porosity information. So gravimetric vapor sorption apparatus, it works typically in dynamic mode. So basically we flow the gases and vapors over the sample, and we measure the value of the sample at a constant temperature. The benefits of the gravimetric systems are more, they tend to be used more in industry. So if you want to understand the process at more relevant industrial conditions, so you tend to go for gravimetric methods because they typically operate at ambient to high temperatures, whereas volumetric, they go down to 7,000 Kelvin. And for some of the, most of the absorbents are used at the atmospheric pressure or higher pressures, or at room ambient temperatures or high temperatures. So you're not going to use the zeolites at 77 Kelvin. Now, there is many gravimetric absorption analyzers, and they usually operate at atmospheric pressure or ambient pressure. What it means, they have a nitrogen and air as a carrier gas, and which is also then used for generation of the vapors. But sometimes, in many cases, these porous materials require actually high temperature and high vacuum to actually be completely outgassed or to remove completely dissolved molecules. And this can be only achieved in the vacuum system. So when you can apply vacuum in high temperature, because traditional flow methods and conventional heating is not sufficient. So when you use a nitrogen, you're basically pushing the molecules, and it's not as powerful like when you're pulling the molecules when you use the vacuum. So vacuum gravimetric system, they also guarantee clean environment and dry environment for, let's say, moisture, air or moisture sensitive. What it means, if your sample react with the air, so some of the MOFs they do. So if you work under the vacuum, so you don't have to worry about these side effects of what might happen with my MOFs if it's react with 400 ppm CO2, which might go to a different phase. The other big benefit is a solid water vapor or organic vapor gas absorption. So what it means, we measure vapor pressure of water under vacuum. And this is done, we measure directly by using the baratron. So there is no effect of carrier gas like nitrogen and air or absorption process. Also, we probe this system molecule, probe molecules, probe solid surfaces under real conditions. This will also allows us to reach phase equilibriums. In terms of catalyst, what is powerful about this system is allows you to understand the pore structure of the material. So most of the zeolites were well-defined cages and pore sizes. So now, if you select the right type of the molecules, you can understand about whether the size of the pores is sufficiently big for the molecules to go into the pores, or if it's too small, so the molecules is going to be too big to get absorbed into the pores. So in that case, it's going to be only absorbed out the walls of the pore structure. So what information you can get, let's say, for this gravimetric vapor sorption analysis? So first is drying curve. So basically, again, if you compare to volumetric system, so you can see in real time, the drying process. What it means, so you can see how is the moisture removed from the sample of this absorption species, and whether you actually achieve is constant mass loss. So at certain time, once you completely dry the sample, your mass shouldn't change. So instead of this can be done, the drying process is done almost in situ. Also, we look at the absorption dissolption kinetics. So when we introduce vapors, we want to show how fast material dissolve the water. So we want to see we can calculate the diffusion coefficients. From the absorption data, then we can calculate the isotope. The system is also capable of performing the isobars. So we keep the temperature we vary the temperature, but we keep the pressure constant. And from isotope data, we can calculate also the surface area. So if you have right type of isotopes, and in a molecule there is no physical option takes place, then if you collect all the isotopes at different temperatures, we can calculate the absorption. So here's the picture of a DBS vacuum analyzer. DBS vacuum system is a gravimetric vapor sorption analyzer. So it comes with a PC, set of the dry pump and molecular pump and the temperature enclosure. We call it incubator. This is very important because your sample, paratrols, muscle controllers, everything is inside this temperature control enclosure, operating to the range 10 to 70. So what it means in this temperature range, I can generate vapors up to 90%. We can work with most of the molecules. There is no limit. There are some limits in terms of the toxicity and corrosivity, how corrosive materials it can be, so it can damage the pumps. So if you open the door, what you see, you can see clearly this vacuum stand made of stainless steel. And what you see under the HUD, you have the balance. On the left-hand side is the sample, on the right is reference side, so it is true symmetrical balance. And what you see around the sample side, we have high temperature preheater, which allows to heat up the sample up to 400 degrees. And then we have two muscle controllers for delivering vapors and gases. So this allows us to study, let's say, co-adsorption. So I can do water adsorption isotope, pure CO2 adsorption up to 1 bar on the same sample. And then I can look at the effects of the moisture or effect of the CO2 adsorption in the presence of the moisture. So these simple setups allows you to run the experiment for weeks without actually opening the sample because of the ability to actually in situ regenerate the sample. So we have 2 bar atmosphere. Now the system works in 2 different operational modes. So we can have dynamic mode and the static mode. So dynamic mode is basically that we flow small amount of vapors over the sample while we keep the top pressure constant. So we set the flow rates, let's say on MFC1 to 5 ccm. We set the partial pressure of water, let's say 10% POP naught. So what it means, we measure absolute pressure. So we need to know saturation pressure of water 25 degrees, which is 23.8 torr. So if you want 10%, it means 2.38 torr absolute pressure. So this valve closes, we fill up the chamber with water vapor. When the set pressure is reached, then there's continuous feedback between butterfly valve and paratrough. When the set goes above the set pressure, valve receives the feedback and opens a little bit. So in that case, so we flow in the vapors over the sample while we keep this pressure constant. And the butterfly valve exhaust is actually connected to sets of the pump. So what it means, when the pressure is too high, the valve opens, the vacuum pumps sucks out the molecules of the system and the pressure reduced. And this way, we can flow the molecules over the sample while we keep the pressure constant. At the same time, we continuously record the change in the mass. So we have this ultra balance here. So we have two baratrons to measure absolute pressure of vapors, gases, organic molecules. We have another high pressure gauge for measuring high vacuum, so that the double molecular pump is fused. And on the sample side, as measures the preheater. So this is what I describe is the dynamic mode. But the benefits of dynamic mode is that we can go to extremely low partial pressures to ppm level. So lowest pressure we can control and measure is 5 millitorr. Okay, and then you have to recalculate how much it is in the pre-op or ppm level. And so it allows, you can also go in dynamic mode gas absorption, you have to take up to 1 bar. We also can perform static mode. So we can do binary co-adsorption measurements. So what it means, during the static measurements, the butterfly valve is always closed. So then I'm using my upstream, MSC1 or MSC2, to actually introduce vapors or gases. While the mass, the balance is going to be continuously measure the changes in the mass. Now, so how the actually typical experiment works. So first, you load the sample. So this can be pellets, beads, powders. And then the sample is loaded in this metal pan, which is suspended and then hang down wire suspended from the balance beam. So what's happening in this stage, we close the chamber and then we pull high vacuum. So during this stage, we're going to actually outgas the material. So on the right hand side, I get my kinetic plot from the entire experiment. So this can be used to actually understand the actual contours on the left hand side. So during the drying stage, what you observe is the mass loss. So sample is losing the mass. So when the sample is brought to the absorption temperature, so let's say go from 300 degrees to 25 degrees, so you cool down to 25 on the high vacuum, sample is at 25 degrees, so I can introduce my vapor molecules. So in that case, I set the partial pressure, so downstream close, fill up the chamber with water molecules, sample already start absorbing the materials. So what's happening here? The mass starts going up. When the set pressure, when the pressure inside the chamber is above the set pressure, the valve opens. At a certain, after a few seconds, we actually reach the steady state that we have the continuous flux of vapor molecule or gas molecules on the sample while we just measuring the sample mass. So what's happening here, because the adsorption process is quite slow, so in this stage, we just waiting for the mass equilibrium. And mass equilibrium is defined by flatness of this line. So in our case, we use mass equilibrium criteria, which are called DMDT. So we typically set DMD to, let's say, 0.003% per minute for duration of 10 minutes. So what it means, when the threshold value is met, the software moves automatically to the next stage. So when the software moves to the next stage, the partial pressure increase, and again, we're waiting mass equilibrium criteria. And as you can see from the steps here, so after initial steps, the subsequent steps, partial pressure of water, and the mass equilibrium steps are relatively fast. So what it means, when I'm stepping up, the partial pressure from 0 to 90% is called adsorption. When I step down, my partial pressure of water from 90 to 0% is called desorption. So in this process, I'm removing the water molecules from the sample, and the sample is just losing the, as a result, sample is losing the mass. Now, from this mass equilibrium points, the different partial pressures, then we calculate the isotherm. So at the plot here, we have adsorption, desorption isotherms of 30 next to 25 degrees. So on x-axis, you have the partial pressure, P or P naught. So P is the pressure, P or naught is the saturation pressure of the solvent. And on the left-hand side, you have the weight. So in this case, we represent a change in the mass, but this can be then converted to number of moles per gram. So adsorption in red, desorption in blue, and small hysteresis gap is called this. A small gap is called hysteresis. Now let's move to the example of absorption data. So just to demonstrate the level at very low partial pressures. So here we look at the partial pressure control of 2-propanol at 50 degrees. As you can see, at these very low partial pressures, we can actually, you can see more or less straight line. But if you look at the absolute values target and measured P or P naught, so we can go to extremely low values to 0.003, 0.006, and still can detect change in the mass. Okay, so now let's look at the data. So what it looks like. So here's the typical absorption kinetics for 2-propanol at 50 degrees for fiber zeolite. So you can see, so this extreme low P or P naught. So here got in solid blue line is a partial pressure plot. Solid red line is the mass. Okay, so the partial pressure plots you saw in the previous slides. So what you can see at extremely low partial pressures of 2-propanol, I still can get a really good mass signal. And then if you convert this data to isotherms, so you get nice type 4 isotherms with lots of data points in the region of some condensation limits of porosity. Now the same material now was used with the water vapor. Again, on top left, you have the kinetic plot. Again, we look at the very low partial pressures of water. So we went down to 0.02 P or P naught. You get almost 5-8% uptake. So again, you get to look at the type 1 isotherms at 50 degrees for water absorption on the fiber doped zeolite. So what you can see, by varying the different flow molecules, we can get different type of isotherms. So in this case, for water vaporization option, isotherm at 50. For fiber doped glass, I can get nice type 1 isotherms, and I'm able to go to extremely low partial pressures, which we won't be able to obtain, let's say, in the flow systems. If I use 2-propanol at 50 degrees on the same materials, so then I get type 4 isotherms. So basically, depending on the type of molecules you can use, so you can select the isotherms. So from this, let's say we could calculate BET. So for the area. Now, the other application I mentioned about VOCs, we can also use some more exciting molecule, let's say like the benzene, which is not very common in these days in the labs, but we can be replied with the toluene. So here we look at the zeolite Y, and we compare the modified zeolite Y with a commercial zeolite Y, and we look at the base desorption at 25 degrees. So what you see here, so in this turquoise line here, so we can see type 4 we have a lot of type 4 isotherms. So the adsorption with turquoise, desorption in brown. So where is this is the commercial zeolite Y. So what you see, you get nice, you get quite lots of porosity, and also you have some you have the microporous and mesoporous parts in this zeolite. So it's a mixture of both. But by modifying the chemistry of these materials, I can change the porosity. So what I can see, I still get quite lots of microporosity, but also I can completely change the isotherm. So from a typical type 4, you can go to sort of type 4 isotherm with a huge hysteresis, showing that toluene is not actually coming off during the desorption. So by changing the chemistry of the materials, I can actually change the isotherm. So the other way to look at this material. So I don't have to. Now I'm going to briefly talk about the effects of outgassing. temperature on water absorption capacity of Morph 74. And so I want to look at the spend a couple of minutes on the outgassing. So outgassing is quite important for metal organic frameworks, and the selection of correct outgassing temperatures can have profound effects on the absorption capacity. So if the temperature of the outgassing temperature is so low, so you might, for thermally stable material, so basically you can actually incomplete the outgassing. If the temperature is too high, you might destroy the material. So I will give some example of the second type of the outgassing. So here we look at the in-situ drying curve for outgassing of Morph 74 at room temperature and high temperature. So initially we load the material at 1 bar, pull high vacuum, and let it outgas at 25 degrees. So what you can see, you get certain mass loss straight line. But what we did, the system allows us to increase the temperature to 155 degrees a minute. So what you can observe here, you get even a bigger mass flow. So now we can compare. This plot demonstrate the differences in outgassing, which might have basically a big impact on your absorption capacity. Because in both cases, you can see the line is flat, but in terms of outgassing at higher temperatures, you can completely empty the core, so you can remove all these physical molecules, which is not possible using just ambient temperature. Now here we're looking at the Morph 74 water absorption kinetics. So solid red line is the mass, and solid blue line is the partial pressure of water in the vacuum. So throughout my presentation, the red line will be always the mass, and the blue line is going to be always the pressure. So as you can see, we're getting good kinetics, good nice mass equilibrium, manage a lot of pressure steps. As you can see, the stages are different. This suggests that the experiment was done in the MDT mode with the mass equilibrium criteria, because you can do the same experiment in time mode, so you know exactly when the experiment finished, but there is no guarantee you reach the equilibrium. Okay. So now, if you look at the, let's say, desorption isotherms, so what you're looking at here, so we have magnesium Morph 74, and we outgas the material at 150 and 250 degrees. In each case, this fresh sample was used. That's very important. So if I outgas material Morph 74 at 250 degrees, my isotherm is showing adsorption in green, desorption in pink. What you can see here, we have huge hysteresis at quite low capacity. Now the same material, outgas at 150 degrees, shows a little bit adsorption in red, desorption in blue, small hysteresis. First thing what you can see is the differences in the hysteresis gap. So for material outgas at 250 degrees, this suggests the structure was destroyed because hysteresis is huge, and the adsorption capacity, if you look at the low, let's say below 40%, is quite low compared to 150 degrees. Whereas the material outgas at 150 degrees shows clearly the much higher adsorption capacities and much smaller hysteresis. Now, we also functionalize this Morph with tetraethylene pentaimine in order to increase size for CO2 absorption. And what we can see, again, two striking differences. Again, in each experiment, for each experiment, fresh sample was used. So for both outgas at 150 degrees, adsorption in green, desorption in pink, both outgas at 250, adsorption in red, desorption in blue here. What you can see, first, the massive difference in absorption capacities. So Morph outgas at 250 give you almost twice as high absorption capacity, very small hysteresis compared to the same Morph outgas at 250 degrees. Also, in this case, basically we observe a thermal degradation of the Morph because the temperature was too high for this material. So just to see, because the reason I look into this, because we can see sometimes different Morphs for different absorption capacity in the scientific publications, and in many cases can be attributed to the chemistry or preparation methods. But I think we should consider, as in the wider community, to look at also the outgassing conditions, how the materials are treated through this absorption study, because as it can be see here, the effects of the outgassing can be quite significant. I mean, typically you would never outgas more below 150 degrees, above 150 degrees. But again, if you go too low, if you are to say much lower temperatures, again, you're going to see difference in absorption capacity. Here we look at the desorption isotherms up to 1 bar for these two Morphs. So what you can see here, the absorption capacity of Morph 74 is slightly lower compared to more functionalized Morph 74. So the absorption of Morph 74 is red circles and blue circles and blue squares is a Morph 74 absorption capacity up to 1 bar for CO2, And the function of this Morph is black triangles and red rectangular square, black rectangular box. So what you can see is slightly differences. Now again, look at the effect of functionalization and outgassings. So first, if you outgas, you functionalize a Morph is 100% amines. What you can see, and then you look at the effect of outgassing. So as you learned from previous, we had to 250. So basically, you get very low adsorption capacity, about 7%. If you go to 150, you improve absorption capacity for 100% functional amine Morph. But if you go to 115 degrees, so you would expect much higher absorption capacity. You still can improve capacity, but it's not ideal. So then you look at the option to use actually only 1% amines. And in that case, so here the original was 74. So this blue line, this squares here. And the best results we get for Morphs, which was functionalized with 1% of amines and outgas at 150 degrees. So here's basically the message is the effect of functionalization and outgassing temperature can give you different absorption capacities for CO2. Now I'm going to move so Morph, one of the disadvantages of Morphs, or basically not disadvantages, but a little bit challenging for the Morphs is the stability in the presence of water. So here we look at the middle one, we will look at the cycle, the materials exposed to water absorption at 5.6 kilopascal of water. Here we look at the cycle between 40 and 140 degrees. So what we try to see that the Morph maintains the same absorption capacity during the cycling process, but as you can see, the absorption capacity of Morphs goes down. So this suggests the Morph is not very stable in the presence of water by the cycling experiment done. Now we move to the absorption of toxic gases on Morphs. Here look at the, let's say, strontium Morph prepared by Lich Kubara from Nina in Mexico. And look at the absorption kinetics up to 1 bar for SO2. So in this case, you look at a pure SO2 gas. Again, we get nice type isotopes for pure SO2 gas, no hysteresis. Again, we look at the cycling. So in this case, this material was cycled between 0 and 1 bar. So it was 0 was high vacuum, 25 degrees. That was our regeneration step. 1 bar was the absorption, was the exposure to a pure SO2. What you can see here, so we observe constant absorption capacity of this Morph is about 945 plus minus 0.15 millimole per gram. When we material is cycled between 0 and 1 bar of pure CO2. So this is really good Morph. So we can actually achieve good absorption capacity for the Morphs. Now I'm going to explain you, I also briefly touched about the co-adsorption. So basically we can do co-adsorption in dynamic and static mode. So if you do co-adsorption in dynamic mode, so we can do it in 5 or 10% of water. But what we really struggle is that we only get one mass. And that mass data contributes both CO2 and H2O species. So basically, what we do in this case, we collect the pure CO2 absorption isotope at 25 on the left, pure H2 absorption here on the right. We have the curve, and we calculate the Langmuir constant. So now we can employ the absorption solution theory to see actually how much CO2 is absorbed in the presence of 5 and 10% of water. As you would expect, for 13x, the absorption is dominant by the water, so the CO2 absorption is negligible or non-existing. But what it allows us to do actually, if I plot these two values together, plot against my experimental data, so solid blue line, a simulated dotted red line, we can see that we have the good agreements for 5% and 10% of CO2. Lastly, there's the binary competitive absorption. So in this case, you look at the payload, the material, this water vapor, and then we introduce second species on top of it. So this allows us to quantify the amount of each absorb and absorb. So here we look at another material. So here we look at one of the zeolites. So first we outgas the material, then we introduce 6% of water at 70 degrees. Okay, and we wait for the mass equilibrium. So you get mass equilibrium. Then we introduce the pressure. As we introduce pressure, so we need to actually, in order to raise the pressure, we need to introduce second species. So, but we use the CO2. So then we introduce the small amount of CO2 and wait for the mass equilibrium. But we assume absorption and the water CO2, it is not replacing the water molecules. So as we do this and we go up to 30%, so we can obtain, let's say, absorption capacity of this material in the presence of the water at 70 degrees. So if I subtract my initial water uptake here from subsequent water CO2, I get in my curve, absorption curve, where I can see that at 70 degrees, at the, let's say, at the constant loading of water vapor, let's say in this case 6% RH, in the presence of 6% RH, I get about 10% uptake of CO2. So this is all from my side, and I now would like to acknowledge my colleague SMS and also my collaborators from Imperial Professor Williams, from Mexico, Jorge Balmada, and Ilich Ibarra, and also from my MIT colleague who will be working on the Morph samples. And lastly, I would like to thank you for your attention.
Thank you very much, Vlad. That was great. Yes, just to remind our audience, we now have a live Q&A session, so please do raise your hands or alternatively submit your questions in writing in the questions tab. Our first question here, Vlad, they ask, what exactly is very low relative pressure?
So very low relative pressure is the best to express in terms of absolute pressure, as I said, is 5 millitore. Because if you look at the P or P naught, so P naught is the saturation pressure of the solvent. Okay, so that's what will define how low is going to be your ratio. So typically, the lowest partial pressure we can measure is 5 millitore.
Brilliant, thank you. Another question here asks, so in reference to slide 33, they ask, how can you assure 6% water loading shown in the graph? Is that how you set up the parameters, or is some other change led to that?
Okay, so this experiment was done, so this was done in the static mode. So static mode, you have a closed sealed chamber. So there is no, so we basically introduce exactly 6% of water away from the mass equilibrium. So there's going to be 6% of the water in the system, and because the water doesn't have to go anywhere. And when the mass equilibrium is reached with the sample, so what they calculate is the adsorption capacity in millimole per gram. So this is the capacity for the water vapor, but the relative humidity was 6%. Because the short answer is because it's the static mode, we assure there's going to be 6% of water vapor.
Okay, thank you. And a follow-up to our first question there was, is it possible to predetermine the measured relative pressure on the device?
Sorry, I don't understand the question. Predetermine measured relative pressure.
Yes, I believe this way. Yeah. Is it possible to predetermine the measured P-PO on the device?
Oh yeah, because yes, you're right. I mean, because you have to first, before you set these experiments, you need to know your saturation pressure of the solvent. Okay, so then the saturation pressure of the solvent or the water vary with the temperature. So you know your P naught. And in that case, I can calculate my POP naught. Yes, you can predetermine your POP naught before the experiment. But what is really important, the message here, system measure absolute pressures, okay? And what we actually set in the control software is the relative pressure. So yes, you can predetermine POP naught before the experiment as you want. That's possible.
Thank you. A question here asks, compared to the ASAP 2020 or 2040 sorption instrument, what's the advantage of a DBS system? Okay,
this is a good question. Basically, I think the main advantage of the system is, so we are leader in the vapor sorption techniques. So main advantage is, so we can generate accurately water vapor, and we can measure partial pressure water under vacuum very precisely. And the biggest benefit of our system is because everything is in temperature enclosed enclosure, your sample, which allows the sample, the paratrons, mass flow controllers, to be in exactly the same environment. If you look at your a sub product, typically your generation system is add on to your traditional, let's say, BT measurements or nitrogen absorption measurements. Okay. So, I mean, in that case, you might have some cold spots. Secondly, the gravimetric systems, as I said, they are designed to work at ambient temperatures or high temperatures, whereas volumetric systems, historically, they were designed to work only at low temperatures, 77 Kelvin or 87 Kelvin. So I think the main benefit is the gravimetric system or DBS vacuum is more beneficial to the studying of the applications. Plus, when you do, let's say, gas absorption, it's also easier to measure it, let's say CO2 at let's say, under the vacuum in dynamic mode than the static mode. Because if you go to the very low partial pressures, then one of the challenges you have, some of the materials or the walls, they will be source of outgassing molecules which sticks on the sides of the walls, which can be outgassed, and they will contribute to your total pressure, total uptake. So in terms of this gravimetric system, your gas absorption isotherms tend to be more accurate because you flow the gases over the sample, and you don't have any issue, let's say, with those leaks, which are minimal in the both system. But we shouldn't forget the leaks exist because we operate in the high vacuum region, not ultra high vacuum region. So so that's important to remember. And second benefit is that main benefits, let's say, gravimetric over volumetric system when you do vapor absorption or gas absorption is kinetics. In a gravimetric system, you always see the kinetics, so you can see whether you reach the equilibrium. In many volumetric systems, what you see, you hardly get access to the kinetics. So then you don't see the equilibrium data. In some cases, they might release it, but what you really see is usually it points on the screen for your isotherms. And for many of these experiments, especially for these new novel materials, it's quite important to see the kinetics, because I did measure some CO2 absorption, let's say 400 ppm level, and if you don't see the kinetics, it's very hard to understand whether you reach equilibrium or not, because most of these absorption materials, they are absorbing forever. So I think the kinetics is the other important parameter of the, let's say, gravimetric system versus ASAP 2020.
Great, thank you. And I think we have time for just one last question here. So they have asked, when the dual-site Langmuir is used, the assumption is that gas adsorption is Langmuir-like. How correct is this assumption for water and CO2 absorption?
This is a good question. So the modeling techniques, always before you employ any of the modeling techniques, you need to understand your material first. You can't, so the reason we decided for the dual just side Langmuir because it's the best represents the data, but it's not, as I said, the 13 egg is not ideal material. So before we would even start the experiment, we know that the water absorption, CO2 absorption in the present water will be dominated by the water vapor because we're looking at the structure of the materials.
Brilliant. Thank you, Vlad. That is all the questions we have now, Vlad. So thank you very much again for being with us here today to share your findings with us.
Thank you, John.
Brilliant. So we'll now move on to our second speaker for today, who is our very own Meishan Gao from Surface Measurement Systems. Meishan is an application scientist in surface measurement systems. Since joining SMS in 2018, she has been working on surface characterization of solid materials, including fiber, powder, and film samples, using the dynamic vapor sorption and inverse gas chromatography as her main techniques. Meishan obtained her master's degree in chemical engineering at the Imperial College London in 2017, where her research project was focused on investigating the properties of fragrance molecules with solid substrates by diffusion and sorption. She also received her bachelor's degree in chemical technology at the Hong Kong Polytechnic University and in chemistry at Sun Yat-sen University in 2016. So without further ado, I would like to hand over to Meishan to begin her presentation.
Thank you, John, for the introduction. I'm going to share my screen. So I hope you can see it in a second.
Yeah, that's all clear, Meishan.
Okay, perfect. So hello everyone, I'm Meishan. For my presentation, I will focus on a total different technique for the material characterization, but we also based on the sorption technique with a molecule as a probe to interact with the solid material. So the technique I'm introducing today is called Inverse Gas Chromatography, and the instrument perform this technique is the Inverse Gas Chromatography Surface Energy Analyzer. So I will give a brief introduction about the principle and also introduction for the instrument itself. Then we will focus on two of the major properties will be measured with the instrument is the BET surface area as well as the surface energy. So for go in further details, we can then focus on different kind of materials for the application of the inverse gas chromatography for the surface treatment or the formulation studies of the composite material. And I also included one of the porous material we performed with the IGC before for an idea of the IGC applications. So for the inverse gas chromatography, the principle was developed over 60 years ago and is a kind of chromatography technique to study the gas-solid interactions for the surface and the bulk properties. And the first commercial system with the IGC technique is developed in 2009 and especially focusing on the surface energy heterogeneity, but can also mirror some other thermodynamic properties of the solid material. So IGC technique is more focusing on the surface compared to the DBS technique is focused on both of the surface and the bulk. And the difference between the conventional, like the converted GC experiment into an IGC one, the home-built IGC, has a limitation in the kind of reproducibility or the accuracy, while the IGC SEA system is specially designed for this technique that will give a really good reproducibility of the experiment. So the principle of IGC is rather simple. If you're familiar with the analytical GC experiment, you will know we have a kind of solid phase, which is known with different polarity, and then we will inject a mixture of the anode compounds through this column. So from the result, we can see different peaks, and with the retention and the intensity of those peaks, we can then analyze how much or how what's the composition of the injected compounds we have in the front. And for the inverse gas chromatography, so this time we will pack our sample of interest into our column, and then we will select different range of the organic vapors through this column, and there will be only one peak showing up in the result. And from the retention peak and retention volume of this single peak, we can then calculate some of the solid properties with the sample inside the column. So the procedure of the experiment is rather simple. We first need to pack the sample of interest into our column with different amount, and then we need to select a range of different pro molecules for different kind of interactions. So we need to have some non-polar solvents for the dispersive interaction, and we also need some polar solvents for the specific interactions. So for the heterogeneity of the solid material, we need to inject all the pro molecule at a range of different concentrations for the finite and infinite dilutions. And then from the detected signal, we can then calculate the chemical physical property of the solid material in the column. So here's an idea of the IGC SEA system. So we have the gas phase injection with the reservoir on each side of the column of the oven. So we have 6 reservoirs in each drawer that can totally put 12 solvents at the same time. So all the gas molecule will be injected directly from the gas phase, so it's more accurate to control very low concentration of those organic vapors. And in the middle, this blue part here is the column oven. So we have a very uniform temperature distribution throughout the column with the temperature range from 12 to 150 degrees. And there are 2 different sample locations that allow you to put 2 samples at the same time, but run the experiment one by one in sequence. So the carrier gas for the system is either helium or nitrogen. And there is a very useful function with the background humidity controller inside the system that we can also study the humidity effect on those surface properties of the material. So the detector for the system is the flare ionization detector. The FID is really sensitive to the organic vapors. And we do have some safety features of the material of the instrument that we equipped it with the hydrogen and organic vapor leak detector that allow you to detect the concentration of the organic vapor surrounding the system to shut down if there is any safety reasons. And here are some of the samples we packed before with our instrument. That we ran some fiber sample or some powder sample, and we can also run some porous material as well, like active carbon or some Morph material. And the sample preparation for the instrument is rather simple. We just need to put the sample inside our column, and our column is a straight 30 minutes long column with different size of the diameters. So we have the 2, 3, 4 millimeter diameter column for different kind of powder or fiber material. We also have the 10 millimeter interdiameter column for some larger particle size material, like a tablet with some special coating that you don't want to break the tablet into pieces, then we will recommend to use this 10 millimeter column. And the sample amount for the analysis is really depending on the surface area of the material. So typically we can use from 10 milligram up to 2 grams of the sample for the analysis of the experiment. And in case some of the sample has special nature that cannot be breaked into the pieces to put in the column, we also have an additional feature of the film cell that allow you to put some flame sample or the plate sample in the cell to do the analysis with one side of the plate exposing to the vapor molecules. So for example, if you do any kind of surface treatment with a special coating on a plate material, then the film cell is a perfect choice for the analysis. So IGC technique is very versatile for different kind of thermodynamic properties. So we can mirror the list of different properties from the injection of the organic vapor. So if we do a kind of single organic vapor injection, then we can get a full isotherm of the material. Then from the isotherm, if a kind of type 2 or type 4 isotherm, we can then determine the BET surface area of the material. And by choosing different kind of pro molecule for both nonpolar and the polar solvents, we can then get different components of the surface energy of the solid material from the dispersive part as well as the specific or the polar part. And of course, we are injecting the pro molecule at a series of different concentrations. We can also get high energy site as well as the low energy site on the surface, giving a heterogeneity mapping of the surface in case of surface energy. And by injecting of different polar solvents, we can also investigate the acid-base property of the surface. Is it more electron donating group on the surface, or there are more electron accepting group on the surface? And in case of the formulation studies for the composite material, it's very useful to calculate the work of cohesion and adhesion between different components, which is really coming from the surface energy of each individual component. And I do have a case study in the later section that introducing the work of cohesion and its application for the composite materials. And also by varying the temperature as well as the flow of the carrier gas, we can also calculate some other property of the solid material, like the glass transition temperature and humidity, as well as the solubility or the diffusion of the material. So first, the major property measured by the IGC technique is the BET surface area. And here summarized quite a different methodology for the BET determination, which is widely known in the volumetric techniques with nitrogen sorption. And IGC is sitting in the range between 0.1 square meter per gram to 100 square meter per gram. And the major difference between the nitrogen sorption as well as the IGC technique is the condition that we perform the experiment. So with the IGC technique, we will perform the experiment at room temperature and ambient pressure, which really keeps the original nature of the material during the application or the processing without applying with any kind of harsh conditions of vacuum condition or liquid nitrogen temperature. And this is essentially important if for some fragile or sensitive material, like some organic materials, that at some harsh condition, the sample will destructure, the structure will be destroyed or some of the crystal will be collapsed, or the hydration water will be lost during these conditions, while the IGC technique will give the surface area of the practical sample at the real world condition during the application. So just an example with a kind of certificated or the reference BET material that we bought from the market, that is the alpha alumina reference material, CRM171. So we performed the BET surface variance determination with the IGC technique with about 100 milligram of the sample packed into the column. And then we precondition of the sample at 100 degrees for 6 hours. Then we perform the experiment with octane isotherm at 30 degrees. So here we show the octane isotherm for the material, which is a really good type 2 isotherm. Then we can apply exactly the same condition as the volumetric nitrogen sorption with the monolayer coverage. And from the slope of the BET plot and also the intercept, we can then get the sorption constant and the monolayer volume. And we already know the cross-sectional area of the octane molecules, then we can get the surface area of the material. So the reported value for this CRM1710 sample is about 2.95, and we get highly consistent with the BET surface area with the IGC technique. So this is the experiment for this reference material at room temperature and also 0% humidity, which is an ideal condition in the real world that without any humidity at all. And then we perform another study to study how the humidity will affect the surface area of this material. So at 0% humidity, the surface area of this alumina sample is 2.95 square meter per gram. And with the increasing of humidity up to 90% RH, the surface area of this alumina sample drops almost half of the original value at dry condition. So basically, with the humidity increases, the BET surface area of this material drops a lot, and that's because the water molecule is competing the size of the organic vapors and also blocking the available surface area for this kind of material. So for the humidity effect on this material is decreasing with increasing humidity. But it also happens for different kind of material. For example, for some cotton fiber or hair fiber, if the water can go to the bulk structure of that kind of material, then you probably will notice that the surface area is increasing with the humidity. So it's quite interesting to study this kind of humidity effect on the surface area of different kind of material. And the next property could be mirrored with the IGC technique is the surface energy. So surface energy is a property of the solid material very similar to the surface tension of the liquids, and it quantifies the ability of the surface to react to the bulk. And from the Fox theory, it divided into two different parts. So we have the dispersive surface energy, which counts only for the van der Waals interaction. And we also have the specific components for the surface energy, which given from other kind of chemical interaction, like hydrogen bonding, dipole-dipole interactions. And to get those kind of different interactions, we need to use a series of nonpolar probes for some alkenes like hexane, heptane up to nonane, and dipane to get those kind of dispersive surface energy. And we also need to use two monofunctional polar solvents, which is widely used as dichloromethane, ethyl acetate, toluene, and chloroform to get the specific surface energy of the material. So when we add up two different components, then we will get the total surface energy of the material. And we need to measure the surface energy of different kind of material because surface energy is related to quite a lot of thermodynamic properties. So for example, if a sample has higher surface energy, the surface of that material is better for the affinity with water, so it will have a better wettability. And also, if a particle has a higher surface energy, the particle-particle interaction will be higher. That will result in aggregation inside the particle itself. And if we are creating more defect size on the surface, of course, the surface energy will increase, as well as the distribution, the heterogeneity on the surface will increase as well. And if we start in a formulation of different components in the multi-component system, that the surface energy is quite important to predict whether the filler or the coating and the base material is a good affinity between each other. So normally for the analysis of surface energy, we'll inject our pro molecule at different concentration. So when we introduce a very small amount of or the concentration of the organic vapor, it will firstly cover on the low energy side, on the high energy side. And when we gradually increasing the concentration of our organic vapors, then it will gradually cover the low energy side. So we will have the infinite dilution for the high energy side, and then for the finite dilution for the low energy side. And this is quite important because all the surface, the natural material is a kind of heterogeneous surface that we have both the high energy side and the low energy side. So for example, here we have the red surface, which is less variation and is kind of more smooth or less rough than the blue surface. Then we have a less variation between the high energy side and the low energy side. Well, for the blue surface, we have more defect size on the surface, so we can have the high energy side really large variation between the low one. So the distribution of this surface for the surface energy is also wider in the distribution. So here we can tell from the surface energy distribution that which sample is more heterogeneous and which sample is more homogeneous. So for the analysis of surface energy, normally we will inject a series of nonpolar solvents at the same coverages. And then from the retention time of each nonpolar solvent, we can apply the Doris Green method and the Schultz method to get an alkene line here, which normally a linear line. And from the slope and intercept of this linear line, we can then calculate the dispersive surface energy of the solid material. Then we can perform the same experiment at a series of different concentration of different surface coverages. Then we can get the surface energy profile with both the high energy side on the surface as well as the low energy side on the surface. And then for a more illustrative interpretation of the data, we can get a point-by-point integration of this surface energy profile to get a distribution with the x-axis for the surface energy. So we have the high energy side on the right-hand side and the low energy side, which is the majority on the surface on the left-hand side. So then we can compare between the distribution of different material to see the heterogeneity of the solid material. And then we can focus on the applications of the IGC technique. So normally we will do some kind of surface treatment on our material to change the surface energy for a more desirable product. So in order to lower the surface energy, we can physically cover a surface by waxing or coating, or we can introduce some uniform functionalization by the salinization or hydrogenation. Or we can also increase the surface energy that we can introduce a high energy functional group by chemical treatment or oxidization, or we can also increase the surface energy by the sanding or etching, chemical etching. So the first case study I have here is a surface treatment on the mannitol material that we both have the as received non-treated mannitol, and we did a salinization process on our mannitol material. So measure the surface energy of both of the material that we have our energy profile on the right-hand side. So the blue line here is the untreated D-mannitol that is changing with the high energy side at low concentration and then go to the low energy side at high concentration or high coverages. So basically for this untreated D-mannitol, the surface is very heterogeneous with a large variation of the surface energy as a function of surface coverage. And after the treatment, we have the red line for the selenized D-mannitol. So this time, the surface is not changing as the surface coverage, that both the low energy site and the high energy site is almost the same level. The surface of this treated mannitol is more uniform, and also for the selenization, you change the surface energy for a lower value that basically passivate the surface with a more stable flow behavior of this particle material. And to get an easy interpretation of surface energy, we can also plot for this distribution profile. So basically, we can compare for the width of this peak that the blue line for the untreated mannitol is much wider compared to the red line for the treated mannitol, which is much more simpler, that the untreated mannitol is more heterogeneous compared to the uniform treated mannitol. And because the surface of this treated mannitol is more uniform and homogeneous, that also indicating that the coating of this mannitol with the functional group is a kind of completely coating with all the sites on this mannitol is coated with the same level energy of the functional groups. And when we have the surface energy of the material, we can also apply this equation to calculate the cohesive work of the particle between the particle and the particle by the surface energy component. So we have the dispersive surface energy and different components of the specific surface energy. So we can calculate the work of cohesion of each particle, the untreated and the selenized. And if the surface energy is higher, basically the work of cohesion will be higher as well. And the higher work of cohesion always indicative of a higher aggregation tendency of the particle itself. So basically the particle-particle interaction is much more stronger, that will causing the aggregation of the material. So here we, from the previous result, we calculate the selenized D-mannitol is hardly changing with the function of coverages and also having a lower work of cohesion compared to the untreated mannitol, which is the red bar here, is changing with a function of coverage and also very high in the surface work of cohesion. So what we can predict here is the untreated mannitol will have a higher tendency to aggregate compared to the blue bar, the selenized mannitol. And then we proved our prediction with some flowability tests of the same mannitol that we get for the treated D-mannitol is hardly changing with the air flow velocity, that the untreated mannitol is quite unstable flow behavior at low air velocity and shows a significant variability at low air velocity. So basically, the flowability behavior of different kind of particle could be related to the surface energy and also the surface energy distribution of that particle itself by calculating the work of cohesion as a parameter to predict the flowability behavior of the particle itself. And the next case study is related to a kind of carbon fiber. So carbon fiber is quite useful in case of the medical industry nowadays because of the light in the weight and also the high strength of the carbon fiber itself. And we can always change the nature of the carbon fiber by a kind of sizing procedure, and also different pre-treatment condition will have an effect on the nature of the material as well. So we want to study the sizing effect and also the preconditioning temperature effect on the material with the IGC technique. So we measure the 4 different kinds of carbon fibers, one size and unsized carbon fiber at 30-degree preconditioning and also 120-degree preconditioning. And here's the distribution of the surface energy. So here we find for the red line and the pink line for the unsized carbon fiber, it has a large variation between the high energy site to the low energy site, changing dramatically as a function of the surface coverage. And after sizing, the surface of this carbon fiber passivates, and also the sample becomes more homogeneous with not changing a lot with the surface carriages. And it could be more illustrative in this distribution that the temperature has more effect on the unsized carbon fiber with higher energy for the 120-degree treatment compared to the 30-degree treatment, which probably due to the removal of the contaminant on the surface or also open the energy site, activate the energy site. Well, the sizing agent for the carbon fiber, which is the blue line and the yellow line here, is almost overlapping. That means the sizing agent is acting as a texture layer to pre the carbon fiber inside from the temperature effect, that making the sample or the fiber more stable or more uniform during the applications. And another kind of study for the carbon fiber as well. So we can also study the acid-base property on the surface of this material to study the effect of the treatment. So this time we also have the oxidization procedure added into the carbon fiber. So we have the acid-received carbon fiber, the oxidized carbon fiber, and the oxidized andesized carbon fiber. We measure the surface energy of all three carbon fibers, and then we calculate the work of cohesion. We calculate the Ka-Kb value, acid-base property of this material. So basically here we have the Ka-Kb value from different kind of polar solvent, and the acid-received carbon fiber with the higher Kb value, which indicates a more electrodonating group on the surface for a more basic nature of the original carbon fiber. And by oxidization process for the first two carbon fiber, the Ka value increased a lot. That means we introduce quite a lot of electron accepting group, functional group on the surface. And after sizing, which is the middle column here, the acidity of this carbon fiber becomes less compared to the sample without sizing, so make the sample more uniform or more stable for the application. So basically, the oxidizing in the surface will increase the surface acidity, and which could be detected from the IGC technique for the Ka-Kb values. And the next application for the IGC technique we can use is the formulation studies for the multi-component system. So we can calculate the work of cohesion as we introduced previously for the particles. So we have the dispersive surface energy from each component, and we also have the specific surface energy. And here for the multi-component system, we have the other component, so we can calculate the work of adhesion between unlike bodies. So we have the dispersive surface energy from solid 1 and solid 2, and we have the specific surface energy from two different solids as well. Then we can compare the ratio of between the work of cohesion and adhesion to predict which is the best formulation for different kind of composite material. So the study here, we have different kind of nanofillers, and we want to find out which is the best nanofiller for the polymer matrix to form the reinforced composite material. So we have the carbon nanotubes as received form, and also we have the functionalized carbon nanotube. And then we have the nanoclay sample as received, and also treated nanoclay sample. So we measure the surface energy of 5 different components to find out which two has the best affinity. So here lists the surface energy of all different components. So among the nanocomposites, the nanotube sample is energetically more active due to the aggressive oxidizing of the acid treatment. So this may be introduced more defect size and also shorten the nanotube length. And with a higher surface energy, the greater cohesive forces between the nanotube particles will lead into a poor dispersion or the decreased loading transfer to the nanofillers. And also significantly lower surface energy of the treated nanoclay sample, which indicates of dramatically passivate of the surface with those kind of functionalized treatment on the surfaces of these nanofillers. So from the surface energy, we can then calculate the work of adhesion and the cohesion between the nanofillers and the polymer matrix. So what we find out here is that the ratio between the work of adhesion to cohesion ratio as a very useful indicator for the affinity between the nanofiller and the polymer matrix. So here we have the nanocarbon tube, that the as-received nanotube has a higher adhesive to cohesive ratio, while the functionalized nanoclay sample has a better ratio. So the better the ratio, that means the better affinity between the nanofiller and the polymer matrix, that we predict that those two samples has the best affinity with the polymer matrix and giving a better quality in the final composite material. So these are our predictions before we making into the final product. And here we measure the mechanical performance of the final product to prove our prediction. So here we have the non-treated nanotube sample, and also the treated nanoclay sample with the better tensile strength and also other mechanical performance. That's saying those two fillers are the best choice for the polymer matrix. So here just shows the evidence that the work of adhesion to a cohesion ratio is a very good indicator to predict those kind of formulation studies with the help of the IGC technique. And the last study I have here is for the nanotube again, but for another kind of characterization of different kind of nanotubes. So here we have 3 different kind of nanotubes. The as received sample, a new sample was modified with high temperature treatment at 2000 degrees for 2 hours. And the oxidized sample was modified by the thermal oxidation using some chemicals to confirm, and also it's confirmed by the oxidation content by the other techniques. So we measure the surface energy of each 3 individual components by filling the column of the IGC with about 10 milligrams of the sample, and then we perform the experiment at 100 degrees with a preconditioning at 120 degrees for 2 hours. So the dispersive contribution of the surface energy dominated compared to the specific due to the carbon-carbon interaction, and the combination of the high dispersive surface energy and high surface area given by the sample are very high affinity with the organic vapor. That's why we need to apply very high temperature for those kind of elution times of organic vapors. And all the sample shows to be energetically heterogeneous with respect to the dispersive surface energy. So the surface energy is changing dramatically as a function of the carriages. And the oxidized sample is found to be the most heterogeneous sample with the additional of the functional groups on the surface, which make the surface more rough or more heterogeneous in case of the functional groups. And for the annealed sample, we remove kind of functional groups and the sample becomes more uniform. And then we also measure the specific surface energy that confirms the introduction of the additional oxygen containing polar groups for the oxidized sample. So we have the highest surface energy, specific surface energy for the oxidized sample compared to the as-received sample and the annealed sample. And the acid-based surface energy is clearly raised in the oxidized sample, and the surface energy distribution is clearly more heterogeneous also in comparison to the more homogeneous of as-received and annealed carbon nanotube sample. And the polarity of the carbon nanotube could be calculated from the specific component of surface energy over the total component of surface energy. And here also shows the oxidized sample has the higher polarity, which also indicating it's more hydrophilic in the nature compared to the other sample, which as expected with additional introduction of the oxygen group. And we do have different application notes summaries all the case studies I introduced here today. And if you're interested, I can share with you after the meeting for more details. You can have a look later as well. And There are some other publications involved in the IGC technique for different kind of materials. As a summary for the talk, IGC is a very versatile tool for the material characterization. We can determine the BET surface area, the surface energy, and the heterogeneity of the surface, but can also assess the glass transition temperature, diffusion coefficient, or the solubility parameters as well. And I hope it could be useful for your future research. And thank you very much for your attention. Let me know if you have any questions. Thank you.
Thank you very much, Meishan. Yes, we do have a few questions here coming in. So just to remind our audience, you can submit your questions in writing using the questions tab, or you could raise your hand to ask your question directly. So the first question Meishan just asks, in reference to slide 10, does the column have to be packed properly, or is it fine if due to the particle shape and size there's empty space? Will there be any issue in that case running samples? And also, how different is the data when run? How different will the data be when running using IGC versus regular DVS with the same parameters?
So basically, when we pack the sample into the column, it doesn't matter where is the location of the sample and how uniform is the sample. Basically, the flow of the gas will be flow from the top to the bottom, and the whole column will be assessed. And we will have methane as the reference gas for the dead volume. Then we will calculate the net retention time. So as long as the sample is not blocking the flow of the gas, it doesn't really matter the location of the sample or the density of the sample. It will give exactly the same result. And for the comparison between the IGC and DVS, for example, for the BET surface area, it always gives very similar results, or at least the trend between the sample, which has a larger surface area, which has a lower surface area, is quite similar as well. And we normally using the same pro molecule to determine the BET surface area. So if we are using octane as the pro molecule for IGC technique, we normally do octane isotherm for DBS as well.
Thank you. Someone here asks, can we use IGC SEA for a material with a surface area higher than 100 meters squared per gram?
Unfortunately, that's the limitation of the system itself. So we have a fixed amount of the pro molecule we can inject to the system. So the highest limit for the surface area we can only measure is 100 square meters per gram. But for the higher surface area material, we cannot measure the surface energy. We can measure the surface, we cannot measure the surface area, but we can still measure the surface energy of that material by input the BET surface area beforehand from other technique. So we did some measurement of some other high surface area material like Morph with different treatment with more than 600 square meters per gram. Then we can still clearly see the surface energy differences between the different treatments. That's no problem.
Thank you. Someone asks here, do you have to dilute solvents for the IGC instrument, or does the instrument dilute the organic solvents? If it does, what compound is used for this dilution?
So basically, we don't need to dilute it ourselves. All the injection is automatic injection from the gas phase of the reservoir. So we have each solvent here, and the mass flow controller will be control the carrier gas, which we use is nitrogen or helium for different ratios of these carrier gas and the vapor. And then we will have a calibration of the FID to detect the concentration. So we don't need to do the dilution, but the dilution is performed by helium or the nitrogen carrier gas.
Thank you. And our last question here, they ask, if they've understood correctly, the surface energy distribution is measured by increasing the concentration of injected probes with the assumption of the formation of only a monolayer. What is the maximum percentage of saturation pressure of probes used in this methodology?
So basically, when we measure the surface energy, we normally focusing on the low energy side. Low range, which is the infinite dilution, because in this range, the solvent will interact directly with the solid, more likely for the gas-solid interaction. So here we have the range for the high energy side and the low energy side. So in case of the high concentration of the pro molecule, there will have some other interaction between the pro molecule. So the solvent-solvent interaction is more dominant in this high range. And what we find out is below 20% of the coverages, the surface energy will gradually go to a plateau. So most of the energy profile will end it at 20%. So even though you increase the concentration even further, it will still giving you very similar value as the low energy side. So it's not very necessary to increase that high surface energy coverages, but you can still do that, of course. But at high concentration sites, it's not that accurate because the solvent is not interact only with the solid itself. I hope that answers your question.
That's brilliant. Thank you, Meishan. I think we have to move on to our next speaker now, but thank you so much, Meishan, for being with us today and for answering the questions from our audience.
Thank you.
Thank you. Yes, thank you again to Meishan Gao for presenting. And that brings us to our final speaker for today. And we are very happy and fortunate to have with us Dr. Xiaolei Fan from the University of Manchester. Dr. Fan received his PhD. Oh, hi, Dr. Fan. I'll just give you a quick hint of who Dr. Fan, so we all know who we're listening to. Dr. Fan received his PhD in chemical engineering from the University of Bath in 2010. And then from 2010 to 13, he took his postdoctoral positions at the University of Warwick and Cambridge, focusing on the research in heterogeneous catalysis and reaction engineering. Currently, he is a reader in the Department of Chemical Engineering at the University of Manchester, where his research broadly encompasses the heterogeneous catalysis, porous materials, catalytic reaction engineering, process intensification, and structured catalysis reactors. So just because we're just to make sure we don't have to cut short anyone who wants to have questions at the end, we'll pass over now to Dr. Fan to begin his presentation.
Thank you, John. So I can show my screen now. Okay. Can I see it now?
Yes, we can see your screen. Perfect.
Okay, thank you, John, very much. Thank you very much for the kind invitation. Also, a very kind introduction about myself. So, good afternoon, everyone. And I'm Xiaolei Fan from the University of Manchester. So, it's a great pleasure to give a quite high-level presentation about my research in porous materials for catalysis and absorption. I think the previous two colleagues from SMS gave quite detailed, technical detailed information about different technologies. But for my presentation, it's going to be quite high level. Okay, so my presentation today basically will have three parts. And the first one, I will give a very brief introduction about my current research. And the second one, I would like to give a case study of using the post-synthetic modification of zeolites for catalysis. We basically develop a new energy efficient methods for making mesoporous zeolites for catalytic applications. And the third one is I would like to talk about my collaboration with SMS, is about the water vapor sorption assessment for metal organic frameworks. And most importantly, actually, is based on this piece of work, initially the collaboration with SMS, and the findings we produce actually inspired me to do lots of different other research, which are quite interesting. I think this is quite important part for being academic, is always due to have the curiosity based on the finding and to keep expanding the boundary of the science and technology. So now let's get started about talk about my current research. So John has said, like, I previously working on heterogeneous catalysis, and in 2013, I joined the University of Manchester. Basically, I started my independent career, and therefore I would like to stay away from my previous research with supervisors in catalysis. So I decided to to basically focus on the porous materials, which I found very fascinating because when I do the heterogeneous catalysis, I always use the porous materials as the support. Back to the time it was the carbon. And then when I start my independent career, I focus on zeolites and morphs. And my research actually is quite wide in this area. It's including the synthesis, also modification. Quite often it's about the post-modification of zeolitic materials for catalytic applications. But I also done some research in morphs, which I'm going to introduce later on. And then think about their applications. And this part actually include both the zeolite chemistry, also the morphs catalyzed reactions, and also separation. So this is the first part of my research about porous materials. Therefore, the sorption is very important for me to fully understand about the properties, the porous properties of the materials we developed, also modified in the lab. And the second part actually is quite recent and is about the plasma catalysis. But all of this catalyst actually is developed using the porous materials. This is quite recent. It started from 2019. Is a work I'm going to discuss in more details later on. And then actually, there are lots of people, colleagues, working in the plasma catalysis because they can activate some very tough chemistry under mild conditions. And it's very promising technique for this kind of low energy consumption manufacturing of chemicals. But actually, there are lots of colleagues focusing on different aspects of the non-thermal plasma catalysis. For myself, we focus on how exactly we use porous materials to design new catalysts for this kind of new technology. And then also another part of my research is quite traditional. It's also based on porous materials, but this time actually is kind of cellular materials, the foams, as you can see over here. And this kind of materials basically can be used either for separation or for catalysis. For me, we did lots of things, try to functionalize the surface of the silicon carbide foams using zeolites, also other catalysts, which will be used for catalytic application. And the good thing of using this kind of structure compared to the conventional packed bed is because we can try to enhance the mass and heat transfer across the foam structure. And therefore, we try to reduce the effects from the transfer steps, and which can help to render the intrinsic property of those coated catalysts compared to the packed bed. Recently, I found my interest in the biorefinery, which involves many catalytic chemistries, and some of them actually also catalyzed by zeolites. Like, for example, we have the rational design of catalysts for converting the fatty acid to aviation fuels. And this is quite recent research. And I have a major grant funded by European Commission. And this is also one of the main drive for me to do the research into the catalytic biorefinery, which try to answer some of the challenges imposed by the current sustainability call. And that's pretty much I'm doing right now. My current research group have 18 PhD and research assistants, also visiting PhD students, and from 5 different countries, but mainly from China. And this photo actually is taken just before the lockdown 2 years ago. And this one is done last summer. I graduated 4 PhD students from my group, and they're all of them now still working as postdoc researchers in other UK universities. So now let's discuss a little bit more about the zeolites. Why do we need zeolite to be hierarchical? And also about the new methods we developed for making hierarchical zeolites in my research group. So zeolites, I think the audience should may know about these materials quite well. And basically, they are one. I think they are one of the most important porous materials because they're being used every day. Doesn't matter in our daily life or in the industry, and are highly important. Although there are more than 200 frameworks has been synthesized, but I think in total, I can't remember the exact number, but I think in total there are less than 30 of them zeolites has been practically used heavily for by the industry for the sorption, ion exchange, and it's for catalysis. For catalysis, there are mainly big 5 zeolites, very important, especially for the FAU-Y framework. They basically being used for catalytic cracking applications, producing the gasoline. It's quite important. Zeolites basically have different, it's kind of highly porous materials. They have different subunits, which means by combining them differently, we have different kind of framework and do give us different properties. So zeolites are intrinsically microporous, which means for all the zeolites developed so far, if we define them as zeolites, they always have the pore size smaller than 1.2 nanometer. I think they are highly beneficial, this kind of intrinsic micropores, because they can provide, for separation purposes, they can provide the molecular sieving. And also for catalysis, they can provide specific shape and size selectivity. They're quite important. But actually, the microporous zeolite also have this kind of intrinsic drawback because the pore size are very small. So therefore, they always experience the diffusion limitation and hence have the accessibility issues. So therefore, in the community, we have the concept of developing hierarchical zeolites, which means the zeolites with intrinsic microporous phase. At the same time, they're also connected with the secondary large pores and mainly mesopores. So therefore, we still have the intrinsic microporous phase, microporous zeolite phase to provide the functionality we want from them. But at the same time, we try to dig some highways across this kind of crystal of zeolites and try to enhance the mass transfers. If we do have any bulky molecules diffuse into, they can diffuse through the large pores and being trimmed smaller, then can later go to the small pores. So basically, as far as I know, in catalytic applications, as long as zeolite have the mesopores, they can perform better. But there is also another story about the stability issues, which need to be balanced, considered. There are different ways of making the hierarchical zeolite. Basically, two categories. And one is called bottom-up ones, which mainly based on the templating methods. You can use the hard template, soft templates, and therefore scaffolding the large pores during the zeolite synthesis is bottom-up approach. The other one is called top-down. Top-down means we do the normal synthesis of zeolite to have the bulk zeolite first, and therefore we do the post-synthetic treatment and try to generate excuse me, the large pores. But this method actually is very practical because it's used heavily by industry because it's quite cost effective. For the bottom-up approach, normally uses the templating, especially soft templates. They are very effective to give us beautiful materials, but they're quite expensive. Some of the soft templates need special synthesis, can be only produced in smaller amount. And then most importantly, actually, after the scaffolding, we have to remove them. And therefore, the calcination of the synthesized zeolite can give us some very toxic flue gas, which is not very ideal. So there are different ways of doing the post-synthetic treatment of zeolites. Especially like if we show the framework before over here, as you can see, to do the post-treatment, I will try to damage some of the frameworks by the deamination, also desilication, and therefore we'll be able to create some mesopores out of it. And the different ways of doing this, you can use the acid leaching, base washing, and the calcination, steaming, etc., etc. But for my research group, we focus on another mild condition treatment. It's basically based on complexation. It's used the chelating agent, for example, the EDTA. You use chelating agent basically try to treat the zeolite and therefore try to remove some of the framework aluminum out and therefore can form the mesopores. And we have this work has been proposed quite early, and I think in early roughly 2005. And there another ETH group revisited this method and then further developed it, which was very convenient. But the main issue is after detailed analysis of the mechanism, we found basically the complexation steps for deamination to create a hierarchical structure, they have 2 steps. And the first one is hydrolysis, which means we have to work with water and then basically hydrolyze the framework structure to lose the framework aluminum. And accordingly, the complexation would chip in to try to remove the framework aluminum. So basically, the first step of hydrolysis actually taking hours, and making the whole treatment have to be ranged in around 6 to 24 hours at 100 degrees Celsius. And I think about like how can we try to improve this method? Since this one is the rate limiting step, then is it possible for us to try to speed up this process? And then we found a paper like a research in other areas. So people using microwave alkylating agent to try to extract metals from the rocks, and they found it's very effective. And we think about if they can do that, we potentially can also do the same for zeolites. And therefore we tried it and it worked. So as you can see, here we showed the table about the development of the materials. The naming of the materials, the HT means the conventional hydrothermal methods, which means it takes 6 hours at 100 degrees Celsius. And we use the microwave ones method to do it. So the ABC representing the concentration of the chelating agent we use, the treatment time, also the temperature. So we found out basically the method is very, very effective. At 100 degrees Celsius, we keep reducing the treatment time to 1 minute, and it's still very effective to produce the hierarchical zeolite with significant mesoporous features, like mesopore volume, also the external surface area. And also, if we try to reduce the temperature to 50 degrees Celsius, it's still very effective. So therefore, this method, the key advantage is we intensify the process and basically reduce the hours from the conventional 6 hours to now to 1 minute, and the temperature can also be reduced. So therefore, we anticipate there is some special interaction happened under the microwave condition between the framework aluminum, also the chelating agent. I'm going to talk about that later about the mechanism. So basically, the material, the whole method can be tuned beautifully, and therefore we can play with about the mesoporosity we would like to have in different materials by varying the treatment conditions. And then also can see over here we keep varying we show about the flexibility of the materials. We can vary the mesoporosity of the materials and also the crystallinity of the materials, and the yield is fully controllable. So therefore we just we patent this work, and then had also received some interest from the industry like Greece in the States, also the Johnson Matthey in the UK. And now we're still discussing about how can we further optimize the method and then try to somehow to think about whether or not this method can be translated into the real use. So as you can see over here, and this one is the parent, the pristine zeolite Y is pure microporous, only with the micropores. But after the treatment, actually, you can see the combination of the mesopores. Also, the crystalline fringe can still be seen over here. Quite important, like if you see from this TEM image, you can see basically the edge of the zeolite Y crystals have been edged out. And this is quite important. This is exactly providing about the entrance, the large entrance for the bulking molecules diffuse into the internal surface of the materials. And also we performed the low voltage SEM analysis. Clearly you can see the working distance of doing this is very low, is only 2 millimeters. Have to be very careful, and therefore we will be able to see clearly after the treatment we develop. You can see there are lots of mesoporous openings, and the openings on the crystal surface of the Y zeolite. And this kind of opening, they provide the entrance for the molecule to during the reaction to try to improve the mass transfer. Accordingly, this something can be quite childish for colleagues in industry, but because the whole development actually was done in my research lab, so I can only do the very preliminary analysis of the economics. So basically, we based on the production of 1 gram hierarchical zeolite Y, on the laboratory scale, and basically we'll see a 21-fold decrease in energy consumption compared to the new methods we develop against the conventional ones. And also, if we do consider the external surface area as the key criterion for the size of the mesoporosity in a hierarchical zeolite, and we found out that for creating 1 square meter external surface area, actually the energy required by the new method is much lower than the conventional one. So, to be in simple word, we just develop new methods which can bring down the energy consumption for making the hierarchical wide zeolite, which is quite important one for industry. And we do believe if we will be able to reduce the energy consumption, and therefore I think all the carbon footprint associated with this method, also the zeolite developed from it, actually can be reduced significantly. And then we tried in the catalytic cracking, and we used the 135-3 isopropylbenzene as a quite bulky one, it's quite bulky molecule, as the model compounds to try to probe about the effectiveness of the mesopores generated by this new method. So we have the parent over here. You can see basically the activation is very fast because this guy actually have the kinetic diameter is much larger than the intrinsic pore size of the parent zeolite Y, which is 0.74 nanometer. So therefore, the large molecule potentially can coke outside of the crystal and therefore deactivate it. For the materials prepared using the conventional methods, it's quite effective initially, but at the end they deactivate it. But for the one we prepared using the microwave method, is much more effective and it's anti-deactivation, and also can be seen by by the yield of a BTX, benzene, toluene, and xylene. Actually, the one using the microwave method is much more selective to BTX, which means can be if this one the materials we have can effectively try to crack, remove all those branches from the model compound, as well as the TGA results showing basically the anti-coking performance of the materials prepared by the microwave method is much better. And also because industry showed the interest, and therefore I'll be able to discuss a bit more with them to know what exactly they want. And this side currently is still like in the lab practice, still like multiple steps get involved. So therefore we think about how can we try to reduce the steps in this new microwave methods. And I'll have another student optimize it, basically make it even more simpler without any change. It's quite successful as well. So as you can see over here, we can also produce the hierarchical zeolites by using these simplified methods. And also we found out basically this method is actually it's quite interesting because we're playing with the process parameter. We'll be able to direct the selectivities of the cracking process. This is quite interesting. We're still like investigating this aspect, and the work has been published yet. This is some preliminary results. And also for other type of zeolites, we can show you like, for example, the beta zeolite can also be successfully deeliminated by the microwave methods. And it's quite interesting because after deelimination, you can see the beta zeolite compared to the parent is very hydrophilic. It's quite siliceous. So therefore, and this kind of beta zeolite can be quite useful for potential adsorption applications in presence of water vapor. So this is something I'm planning to keep working with SMS later on. We just try to find time to plan a trip to London and to visit the lab over there. And then I think that's pretty much like a quick summary of my research in zeolite research. So now let's move to the next one, is water vapor sorption morphs and the research inspired by it. So the morphs, because I'm not trained as inorganic chemist, so I do not do synthesis of morphs. I do not do new structures. As an engineer, I prefer to work with existing material and think about how can we do something to try to improve the materials. So the materials I'm working with is the COBTC or CASK1, developed by Hong Kong University of Science Technology. And basically, it's quite interesting Morph. They have the copper, which is connected by the benzene 135 tricapsylate acid, and therefore give us this kind of highly porous structure. So you have the a copper dimer over here. And basically, they are very interesting materials. And most importantly, actually, this cask 1 Morph, actually, they're commercially available. I think in Belfast, there is a company can use a dry method to produce it, and they're reasonably cheap now. And so therefore, I decided to work on these materials. Initially, I have a student working on these materials for gas absorption, mainly for CO2. And then we try to simulate about the absorption of CO2 from the flue gas, which is CO2 is quite dilute, it's only roughly 10%, and there are lots of water vapor get involved. So therefore, we like to study about the water vapor stability. And this is a when we use the DBS system to try to measure the water absorption behavior of this Morph. As you can see, this is a quite nice figure to show the water vapor absorption stages and also the corresponding the partial pressure used during the experiments. You can see the experiment is quite lengthy, but do give us a very comprehensive information, for example, the isotherm, to understand how exactly the materials behave in this kind of like humid conditions. And this work is quite interesting because based on that, we done lots of experiments using DBS. They are very, as I said, it's very time consuming. But the good thing is we know basically the material is water is hydrothermally not stable. So therefore, the key information from this work is we try to use the DBS to assess about the window of this material to be stable under different conditions. And this is the temperature actually was limited by our old DBS system. I think maximum they can only go for 50. So therefore, with this kind of window, we do provide some information. If you want to use the materials in practice, then you have to try to make sure you design a process to host the materials, because this material have some very interesting property. Simply because the copper center over here, they can bind the CO2 selectively, but compared to the water, they prefer to bind water more selectively. So there are some interesting applications. So based on the water vapor application, and they inspired us to do further research. The first thing is first research. I give you two examples. The first one would be if this one is hydrophilic, the materials, he prefers to bind water, and water are going to damage the framework. So what can we do? Is it possible for us to make it as hydrophobic? So therefore, my previous PhD student, she has an idea saying, can we use glycine? It's a very simple amino acid, and have carboxylic acid also have the amine group. So her idea is basically we try to use the glycine, which is dirt cheap, and basically try to dope the materials. Hopefully, we have the carboxylic acid can interact with the copper center, and then at the same time, for CO2 application, the amine group can still interact with CO2. So as you can see, basically, based on the water vapor absorption, after modification using this very simple method, we make the material hydrophobic. And this is the parent is still like hydrophilic. So therefore, at high temperature, during the water vapor absorption, we have the collapse of the framework. But after modification, it becomes hydrophilic. And this is something quite interesting. But the method is very, very, very simple. And this is quite important for some potential practical uses. And also we compare about the CO2 absorption performance actually is also quite interesting, quite comparable. So therefore we are quite successful by developing this kind of very simple method to make the hydrophilic copper Morph into a hydrophobic copper Morph. And the other one, when we do this water vapor absorption inspired me is, as you can see, basically the whole framework have the highly dispersed copper metal size, and they are not saturated. That's the reason they are highly selective to bind the polar molecules. So if they like the water very much, then they are copper as well. Intrinsically, I think I have an idea they should be very good water gas shift reaction catalysts. because low temperature water gas shift actually just use the copper catalyst, and the reaction have the CO2. So which means the site combined water should be very good catalyst. But the thing is, this Morph actually does not like water because water can damage it. And for water gas shift, at least we need to use 200 or 300 degrees Celsius to activate the reaction. So therefore, in theory, this is a very good catalyst for water gas shift, but in practice, this is not going to happen because we're going to have water going to sit over here before the copper to work as catalyst. Basically, at high temperatures, the water will damage it. So which means under conventional thermal condition, this kind of, as I said, dream catalyst is not going to work for the reaction. So therefore, I have other colleagues working on non-thermal plasma. This is the work done back in 2018, I think. And then we said, if we use non-thermal plasma to activate this, well, we potentially can basically activate the water in the gas phase. And therefore, we can preserve the activity of the Morphs and make sure that this reaction will happen. And this time, we don't need any heating. We don't need any heat. So which means we can remain the activity, also stability of the Morph materials for some interesting reactions. And therefore, I think this can be the solution. And we tried it. And first thing, before we tried it, basically, we tried to use non-thermal plasma to treat the cask one. We need to make sure like non-thermal plasma quite high energy field. We don't want to damage this kind of Morph material, which is hybrid, like organic, inorganic combination. So tried it, and basically we found out we only give you the selected characterization. We show that basically doesn't matter about the treatment of non-thermal plasma treatment. We can retain the physical, also chemical properties of the Morphs after the treatment, and therefore have the confidence to go ahead for the catalytic experiment. And basically, we show that basically by using this material, indeed, is a very good catalyst. Okay, and compare with this kind. This is the pure plasma system with the inner packing, and this is the Xiaolei catalyst. Also, as a control experiment to show the porous materials can enhance the plasma activation. Here is the thermal case. Basically, compared to the one under plasma condition, it's not comparable at all. And we also did some in situ study to understand what exactly happened. But most important, this work is actually about, we try to prove this is surface reaction, because catalysis have to be surface reactions. If we have the Morphs packed into the non-thermal plasma system and basically enhance the plasma discharge and therefore enhance the gas phase conversion of CO and water to hydrogen and CO2, then this is not catalysis. Because what we want is the copper metal size in the Morph to do the work. So therefore, develop in situ drift cell and to show basically, as you can see, when we have the plasma on and increase the applied voltage, we can clearly see the surface of the catalyst changing. And those kind of changes telling us the information about how the surface evolution of the intermediates and the products, etc. So therefore, by using this in situ work, we prove that this is indeed a catalysis, a catalyst facilitated by a good catalyst under plasma condition. This is quite important. And I think that's pretty much everything I would like to share today. And to conclude my presentation today is, one is I think porous materials such as zeolites and Morphs, they are very, very important. And zeolites are highly practical and Morphs, they are highly versatile. And both of them can help us to understand quite a lot of things. And also the absorption analysis is ultimately very important to assess their properties. And also, like based on the DBS system, although it's a very old one, actually we got some quite interesting results on the Morph material, which also inspired some continuation of interesting research, as I showed over here. So therefore, I would like to thank all my hardworking students. Now they all have PhDs and working elsewhere, who I contribute to the work, and my dear colleague from Manchester, also China, who helped quite a lot during the project. Also, all the funding agencies support my research. And also, again, thank you for the surface measurement systems. And I've been working with these colleagues for a while. And thanks for the invitation. And then now I think I can take questions. Yeah.
Thank you very much, Dr. Fan. That was a really great presentation, so thank you. Yes, if everyone who has any questions for Dr. Fan, please submit them in writing or raise your hand now. We have our first one here, and they have asked, have you looked at co-adsorption for HKUST1 with water and CO2? How does this affect its catalytic ability?
No, I haven't tried that yet. I haven't tried that yet. I think this is because we use the cask1 or COBTC for two different purposes. One is for the simulating about the CO2 removal from flue gas, and this is where we start using DBS system to try to assess the stability of the material. But the other one for catalysis actually is water gas shift reaction, is the reaction between CO and water, combining CO and water to convert them into hydrogen and CO2.
Thank you. And another question here with a reference to something you showed on page 21. They ask, the copper Morph before coated, why is there a mass drop at 20% relative humidity?
Which one is this one you mentioning?
Page 21. They ask, yeah, for the copper Morph before it's coated.
Before coated, right?
Yeah.
Before coated, the mass drop is basically, this is due to the collapse of the framework during the water vapor absorption at high temperature. So as you can see, basically, initially, at high temperature can damage the Morph significantly. If we try to go back to previous slides, you can see if we do this at roughly 25 degrees Celsius room temperature, the Morph there, they're doing okay. We have more or less the full adsorption and kind of full desorption, but still have some water kept in the framework. But if we try to do at relatively higher temperature, you can see the spikes over here indicating the framework has been damaged. And this is permanent. So if we keep increasing the adsorption time, go to the 40 hours, we see basically a sudden drop of the mass, which means the framework is damaged and the vapor has been released out, causing the loss of the mass of the adsorbent. Yeah, that's the reason.
Brilliant, thank you. We'll just wait a few more moments in case anyone has any further questions.
Yep.
Someone has asked here. Oh yes, someone has asked here. What problems do you see, if any, in the recovery of these materials for future use?
You mean the Morphs, right?
I believe so. Yes.
I think there is some research on this specific material. Remember, there is a Chinese group, a Hong Kong group, I can't remember. They have developed some methods which can basically, if you do have the damaged cask1 materials, and they have developed some methods basically to recover it back partially. So there's some relevant research in this. Yeah. But maybe the quality of the recovered Morphs can be jeopardized to a certain extent. Yeah.
Thank you. We have a question here. Have you tried these tests with metals other than copper?
Other group, basically, we tried this one first, and then the student who conducted this work went to our chemistry group, and we have a Morphs group over there. They done further work on this in this area, I'm basically showing about basically the combination we developed over here actually is generic. So for my group, I didn't follow up this direction because as I said, I'm not expert in Morphs. But there are two other groups using other Morphs based on other metals for other different catalysis because they have developed the Morphs which have the selective absorption of the NOx. So they use that based on that combining the plasma activation, they show that the NOx is also possible based on the combination Morphs plus the non-thermal plasma. Yeah.
And I think we have our last question here. They ask, since most of the reactions are aqueous, so it is a challenge to work with biological systems and biodiesel reaction. What's the solution to this problem?
Sorry, can you repeat that again, John? The question.
Of course. Since most of the reactions are aqueous, so therefore being a challenge to work with biological systems and the biodiesel reaction, what would be the solution to this problem?
Direct answer, I don't know because I personally have never worked with in the bio system. I kind of can understand the question. I think the colleague asking like basically currently for the bio process basically are the mainstream for producing this kind of bio-based chemicals. And for my research, actually, we only focused on we assume we have some intermediate from the biomass already obtained from other processes, and then we do the further upgrading of them. So even for the biodiesel, for the biofuel production, we assume we have very cheap fatty acid available now, and then how can we try to use the chemical catalysis to convert them into fuels which can be used by airplane or by car. This is our scenario. Yeah. But how to like combining the whole process together, you have the fermentation maybe to produce the bio intermediate, which can be further processed the downstream. I don't know. Yep.
Okay. That questioner has actually raised their hand, so I think they may have a follow-up for that. So, Ferduous, I have unmuted your microphone if you would like to ask the question directly.
Hello, sir. I would like to ask you that. Hello, sir. Are you able to hear me?
Yeah, I can hear you. Yeah, I can hear you.
So, have you tried with bimetallic elements like if we talk about copper and silver or copper and zinc to embed it in your structure, copper zinc morphs, or just you tried with only single metal monometallic morphs?
Yeah, now only single metal. I didn't try the bimetallic ones. And I did some work like bimetallic ones, but basically we use the morph as the support and then to support another metal on it. But at the microscopic level, how exactly we can graft the intrinsic metal centers using another metal, I haven't tried that yet. Yeah.
Sir, is it possible to collaborate with you to do further research in this area?
Yeah, I'm quite collaborative. I'm quite collaborative, so always interested in you. Basically my research is driven by curiosity. So as long as we have some interesting case, I'm open. Yeah.
I found that in your slides, one of the challenges is the aqueous media, as you discussed right now. I mean, you said that the water is one of the problems for the whole stability of the material. So does this mean that this has most application in non-aqueous media?
No, my personal opinion on this is we cannot avoid a moisturized system or humid system in practice. So for materials, they're supposed to be very robust. Doesn't matter the dry condition or wet condition. So basically for my research, I only showing like the current materials, for example, morphs, they can be very good in the labs, but for practical application, they're gonna have some limitations.
Exactly.
Especially dealing with the water. Yeah.
Yes.
Yeah.
So
Therefore, I think it's one of the star materials now, morphs. And in scientific field, there are so many interesting research going on this material. I think with the further development effort, definitely we're going to have some quite robust morphs in the market and for some interesting application. But I think that now the most important thing for them is, again, they're quite expensive.
exactly.
And the other one is just,
well, do you think any kind of material that we can use as a base material so that we can reduce the cost for their manufacturing or production?
I didn't follow up this direction recently. I think in the past, the main problem for this material is about synthesis. They use a large amount of solvent, organic ones.
Okay.
So therefore, making the environmental impact, also the life cycle of the material very bad. So the reason I say, like, currently there is a UK company, they can do this, is they have the dry method, which can reduce the use of solvent significantly, and therefore they drive the cost down. But they are still relatively expensive compared to zeolite. Yep.
Okay. Thank you for the answer. Thank you, sir.
Yeah. Thank you.
Very much, Vidi's. And I think we just have one last question, so we'll give them an answer while they're here, just before we leave. So the last question is, how did you measure the specific pore volume of micropore volume and mesopore volume?
This will have the standard methods. Basically, I think in my case, I haven't used any SMS system for the determining the porosity of my material. You basically just use two types of porosimetry. One is the nitrogen, the other one is argon. So if we try to do the nitrogen, the routine nitrogen absorption, then we can use different models to try to extract the information of BET, the first one. This BET is the first one. And then we try to use the other models. I mean, basically the machine calculated. We just need to make sure the machine used the right equation to do this, then that'll be fine. And then we try to determine about the micropore information. And for the mesopore one, basically, we just use the information on the total, also the micropore one, so we can determine the mesopore one, because the sum of the micro and mesopore volume actually will be the total pore volume. And the same for the specific surface area, because all the porosity was contributed by both the micropores, also mesopores. So we work out the total and then work out the micro, and intrinsically we'll just have the mesopore ones. Yeah.
Right. Well, I think that's all the questions we have, and we have in fact overrun. We've had such an engaged audience, so I think we'll leave it there for today, Dr. Fan. Thank you once again so much, Xiaolei, for joining us and sharing your findings with us today.
Thank you. Thank you, John. Thank you. Yeah.
Thank you. And a big thank you to the rest of our audience for joining us, and to our other speakers today. If you do want to attend any of our events in future, we have 2 upcoming workshops in the middle of May, the information for which is on screen now, and you can find out more about those and sign up free at surfacemeasurementsystems.com. And again, before I leave, I'd like to extend a massive thank you to Dr. Xiaolei Fan and the University of Manchester for being here today with us to share their findings. So thank you all again for joining us. And if you have any queries, please don't hesitate to reach out to marketing@surfacemeasurementsystems.com. Wherever you are, please enjoy the rest of your day. Thank you.